Alrighty. So today our webinar is presented by Mr. David Cockrum with Mead and Hunt, and as we've discussed, his presentation is related to the renovation of Jefferson Barracks Building 29. So, Dave, I will send this presentation to you, and
got it.
You got it. All righty, very good, David. It's the floor is yours.
Okay. Well, thank you very much, David. So Jefferson Barracks, Building 29. This building is in St. Louis at Jefferson Barracks. Jefferson Barracks is located on the south side of St. Louis, and it incorporated multiple different challenges in construction. Sorry, I was getting my computer adjusted, and here we go. So moving on. The AIA Learning Objectives for this presentation are to describe the preservation efforts and the different historic features of the facility, and then to look at the seismic deficiencies and the weaknesses of the structure and what that meant for our project. Then we will discuss the progressive collapse requirements and the anti-terrorism requirements for the project as it was programmed. And then finally, we will discuss the design project and some construction challenges that followed. So the building definitely was historic, and I grew up on a farm in Iowa, and my parents had a lot of old things, but they were not historic. They were just old and they were worn out. And growing up in that fashion led me to have a very low appreciation for historic things. However, when I started on this project, it's very historic, and I quickly learned historic value throughout this project. And so the building is old, but it also has these character-defining features that make up the overall presentation of the building. And we had to preserve those, and then do the anti-terrorism and a progressive collapse and the seismic retrofit and all these things. And at the same time, the goal was to renovate this building to modern office standards with all of the creature comforts, like bathrooms. We couldn't just let them use the outhouse anymore on this. So bathrooms it is, and all of the other things that you expect in a modern office building. So looking at the building and identifying these character-defining features, we see the brick first and foremost. There's brick everywhere, lots of it, and the brick was in pretty good shape. There was no major cracking, and the grout was actually fairly all intact. The outer surfaces of the grout had softened, but it was in good condition. And then, of course, you see these arches on these windows. Every single one of them had an arch, and especially there on the upper stories of the building, you have high arches. Then there's the porches, full-length porches on both of the wings. And then as you raise your eyes toward the ridge of the building, you see the attic ventilators. And those are the actual attic ventilators as they were designed on the original building. Now, of course, this is a unique building, and it's also special because it's part of a campus of buildings, and they call that a historic district. And it's important to preserve the history of the building by focusing on all these smaller features and preserving the features as they are accurately. And then once you do that, the whole overall historic fabric of the building remains intact as it originally was in 1898. And then if you do that on every building within the campus, then the historic district maintains its effect. So moving around to the back side of the building, you see that it's tall, and my first impression on the building was this thing it's kind of majestic, you know. I mean, it's just big and massive. The upper floors of the building, the brick is 3 wythe thick, and so wythe being the stacks of brick that make up the wall, and that comes to 13 inches thick on those upper floors. And then in the lower floors, it was 4 wythe thick, which comes to 17 inches thick. Moving around to the back side of the building, we see limestone foundation. And yes, this is solid limestone, and it is 23 inches thick. So that's even thicker than the brick. Very, very massive and heavy. And as you focus in on the transition from the limestone to the brick, you see the architectural feature there called a water table. And the water table is actually solid limestone through and through for that 23 inches thick. And that it's just an incredible amount of weight. If you think about that, and especially where you have an opening where it spans over the opening and that block is even longer, just really heavy. And so thinking about the construction of this, it's you know, 1898 certainly was before the use of hydraulics to equipment in construction. And so it's interesting to think about potential ways they might have gotten those stones into place with their extreme weight. And they do, over each opening, that is a legitimate stone lintel, original stone lintel. And they were all in great shape. They were not cracked. And so we just had to do tuck pointing on that, and it was completed. So also on the back side, we see the pilasters. It's another character feature of this building. And then, of course, on the very top of the building, I have to point out the masonry chimney. And that brick chimney was certainly unreinforced, and it extends above the roof line by about 14 feet. So that's quite a mass, and it's quite elevated, and certainly poses a seismic issue with an unreinforced brick chimney 14 feet above the roof diaphragm. Now moving to the inside of the building, we see these cast iron columns. And them being on the inside, we thought, well, maybe the State Historic Preservation Office would accept their removal and replacement. However, these have character, these rivulets around at the chair level, and then certainly more detail at the base. And you'll see later how there's a large bell feature at the top that is ornate. And that was a feature that was identified as a must keep. In general, the focus on historic preservation for this building was the exterior and maintaining the aesthetic for the historic district. However, on the interior, there are a few select items, such as these cast iron columns, that were identified for preservation. So cast iron, of course, is pretty good in compression. However, it's always has weaknesses in shear and definitely weak in tension. So, and certainly cast iron from 1898 would be very weak in tension. So looking at the windows again, this is a little closer picture of the arched windows. And I'm pointing these out and also combining with the blast that we'll talk about in a little bit, the blast requirements on the building for anti-terrorism. So that brings us to, well, how do we brace the top of this opening against blast loading with these arches? And then with the high arches on the upper windows, that is a difficult challenge to brace. So that leads us right into the anti-terrorism force protection requirements for the project. The Unified Facilities Criteria are the regulations for government projects, and the UFC for anti-terrorism states in very, very clear terms that our goal and philosophy and driving goal is to minimize mass casualties. It's so important, in fact, that it's actually repeated 11 times I had been reading it, and I just noticed at one point that it seemed like it was repetitious, and so I did a search and identified 11 places where this exact phrase is repeated. And so the philosophy is not that we accept a few people getting killed, and it is not that we accept a lot of people getting injured or hurt. It is that we have to find some reasonable, effective, cost-effective level that we can apply to all of our federal buildings and military buildings across our entire country. So reading into the regulations for anti-terrorism brings you to the selection of your classification. And there's various different classifications for anti-terrorism. And so you start out and you ask, well, does this facility have a sleeping space? And if it has a sleeping space, then you ask if it has families. And certainly if there's a lot of families, we want to protect them. So that is a classification of anti-terrorism for specifically for high occupancy family housing. And then there's low occupancy and billeting. And so there's these different classifications. And I understand that the UFC for anti-terrorism has been changed since this project was designed. However, I'm going to focus on this because it is still actually active for any projects that were not at the 30% level as of last spring when the new UFC came out. So, and then also there is the primary gathering classification and inhabited classification, and these things all play into what you have to do for your facility. Now, in application specifically to Jefferson Barracks Building 29, there was no sleeping space, but it did meet the occupant density levels that classified the building as primary gathering. And with primary gathering, anti-terrorism is always required. Now, there are other measures of anti-terrorism that get applied in different ways. And so then you have to start looking at the criteria of the project that is being proposed. And so then you start with, well, is the project a remodel? And if it is a remodel, then you look at the plant replacement cost and you compare that to the proposed project cost. If you are making a major investment, then of course you want to apply all of the regulations, and so then likewise anti-terrorism regulations are required. The plant replacement cost, just to define that quick, is the cost to build a similar facility with the same function and space as the completed project with the remodel. Then there are other requirements if it's a window replacement project and how that plays into how much of the anti-terrorism requirements are required. Now then moving back up to the remodel portion of the flow diagram, if it is not a remodel, then our next question is well, is this an addition? And if it is an addition, then we couple that with the previous classification of is it a primary gathering occupancy? And of course, if it's a primary gathering, then that indicates that we have a mass number of people, and we certainly are going to, again, minimize mass casualties. So then anti-terrorism, all the anti-terrorism requirements are required. So then if it's not a large addition, then there are different criteria on how much of that is required. Then backing up, if you're not doing a remodel and you're not doing an addition, then you're stuck, because there are loopholes and there's ways in the old UFC where you can get stuck, and it's like, well, okay, I guess I have to go back 3 spaces and figure out exactly what my requirements are. So now in an application to our subject building, it was completely a remodel. And then being a remodel, we then looked at our project cost and compared that to the plant replacement cost. And the cost of renovating this building and with all of the other challenges we had, it certainly exceeded the 50% level. And so anti-terrorism was required again for that. So also in the old UFC, the progressive collapse was triggered by the number of stories. And that trigger is 3 stories. 3 stories or more requires progressive collapse analysis. And this building is 3 stories on the front, and then looking at the back, the basement is exposed. And so the question is, well, is that a story, and would it be actually 4 stories? And the answer is yes. And it's the definition of a story for this purpose is defined in the UFC as any space that has, intended for human occupancy with features such as egress, lights, and ventilation. So this actually comes out as 4 stories for the purpose of progressive collapse analysis. Then our next major challenge was the seismic requirements. And when you look in the regulations for this, it depends on your seismic design category. In the Midwest, a lot of our territory is seismic design category B and sometimes C. And so in St. Louis, we were hoping for C, and the initial geotechnical report came back and told us, well, no, this is seismic design category D. And at that point, that would have been a tremendous amount more work than we had forecast. So we opted to get the site-specific geotechnical analysis for seismic demand, and that lowered the seismic design category back down to C. Regardless, the regulations still triggered the seismic retrofit. In category C, you have a 50% trigger, which means that you're going to compare your project cost to 50% of the plant replacement cost. And there again, we were exceeding that. And so this triggered the seismic retrofit for building 29. When that is triggered, the regulations point us to a document called RP8. And RP8 then directly just redirects us to ASCE 41. And the current version of ASCE 41 is the 2013 release. And in that, it's a design standard and it's a material standard, both all combined in one, and that it pulls on our concrete design and our steel design. However, it really has different provisions than our standard building code and our standard material designs, because it is intended to reduce the cost for seismic retrofits. The first thing is we take the building code earthquake and we say, no, we're going to use a lower or reduced earthquake, and we're going to design for that. It's an earthquake that we expect more. Rather than the 2% of exceedance in 50 years earthquake, we're going to use a 10% exceedance in 20 years earthquake. And then we are also going to use lower factors of safety on our material strengths. And so we are saying that we are going to use the full strength of the building at the actual more probable earthquake. Now, that's great, because that sounds like it's going to really reduce the cost of the retrofit and the demands on the detailing and everything. However, ASCE 41 is also different from all of our other standards in that it starts with you have to go and document the building in far greater degree than you would even for a new building that we are building today. And so with a building that from 1898 required extensive field investigation and documentation of material conditions and so forth. And then after you get that done, then you analyze it. Well, but the analysis for ASCE 41 is intricate, because it requires that you model that facility precisely. And it goes into greater depth of requirements for our modeling of the facility than we would normally model on a new structure design. So then you get this model, and you put the reduced earthquake on it, and you put the full strength of the materials into it, and then you analyze it. And of course, with a building from 1898 that hasn't been retrofit for this, with seismic design category C, there are things that will break. And then you design your retrofit for those things. And then you have to incorporate those things into your analysis and analyze it all again. And the issue is that when you retrofit a building, it redistributes the forces within the building. And when you have a redistribution of forces, then and you analyze again, then other things break. So then you have to retrofit those. Then you analyze it again, and then you retrofit, and then you analyze, and you can get caught in this vicious cycle of, well, let's just build a solid block of concrete and analyze that and see if that breaks. The way to get out of that never-ending cycle is to predict ahead what is going to fail and retrofit it in anticipation of the forces moving. So that's what we applied to building 29, and that leads us right into our retrofit design. So here is the endoskeleton that we designed and had constructed on the inside of the building. So this is a steel braced frame, and it was erected just inside of the brick. And we selected this for a couple reasons. First, we're in seismic category C, not D. So in C, we can use R equals 3 for our steel frames, and that makes our detailing straightforward. The other option really is to build concrete walls throughout the entire interior where the frame, where we use a steel frame, we could have used concrete walls instead. However, with concrete walls, that adds a lot of mass. And for a building of this height, that creates a lot of overturning force in an earthquake and really exasperates the problems that we already have. So the right solution for this building was a steel endoskeleton. So then the next challenge to design for is blast loading on the building. And blast loading can be resisted by best by a combination of mass and ductility. Ductility is really the stretchiness of the materials, which, you know, with brick, there is none. And so we have no ductility with brick, and really had to do something to make it stretchy, so to speak. And so the endoskeleton provided that, and there was also a stud wall between the frames, which also braced the wall. And so there was a great many more posts than are actually shown here that were placed behind the wall. And with the mass of the walls, it required very little stretchiness because it's a combination of mass and ductility to resist the blast. So then the other part of the anti-terrorism is that progressive collapse. And the major requirement there is that you have to assume that you have a hole blasted into your building anywhere. And so to analyze a structure, following those requirements means that you have to take out one column at a time and analyze. Well, we had 132 columns, so that could lead you to the thinking that you have to analyze the building 132 times. But fortunately, the way it works out with this facility is that any hole that is blasted into the brick, as long as it's near the middle of the wall, it arches over it pretty well. And it's really not that extensive of a problem until you get to the corner. Now, when you have a blast that takes out a corner column or the corner of a building, then you don't have that arching action anymore, and you have to hold the whole corner up somehow. So that was basically done by attaching the walls to the endoskeleton, and then that creates a large tension force that pulls on the frame. And the frame was connected throughout continuously, and it really dissipates that tension force throughout the mass of the building. So that is how we mitigated the progressive collapse issues. So then the next would be to discuss the seismic load path. And seismic is certainly like wind or like blast, but throughout the whole building and applied to the mass. And predominantly, it's a lateral force on the buildings. You do get some upheaval forces in earthquake waves, but the majority of the forces result in a horizontal force. So those horizontal forces act on the walls, which then act on the floor plate. And a floor plate, you know, being a diaphragm, would look like this brown rectangle here. Then that floor plate pushes on the cross braces. Then, of course, the cross braces have to be found on something, and so we had to build a new foundation for underneath the endoskeleton. Now, to maximize usable space in the building, we pushed the endoskeleton right up close to the brick walls. So there in the picture on the left, you see we really pushed it up there as close as we could. And however, the problem with that is that that did not coincide well with where I was able to build concrete walls in the basement. And so I had to develop this corbel on the top of the concrete walls. And unfortunately, a corbel really has very limited strength. And so in order to get the force out of the columns and into the wall, I had to spread the force out with that beam, that horizontal beam on top of the corbel. And so that we called a spreader beam. And in order to attach that to the corbel, we had no ability to use anchor rods. It was just too tight of a configuration, and there's just no room for anchor rods. And so we ended up welding the reinforcing steel directly to the spreader beams. And during design, I was concerned about constructability of this. However, the contractor assured me that they would do it and make it happen. And what they ended up doing was just having it welded ahead of time. And then they just poured the concrete up underneath of that and sloughed it tight. So moving on, I've alluded to these concrete walls in the basement. So here is another detail of how we did that. There's the limestone walls around the entire perimeter and two across the core. And so we sistered those with new concrete walls. And these sister walls were pinned to the limestone with threaded rods in really deep holes with epoxy. And which sounds great and everything, but the issue really is that when you have an old masonry wall like that, you have to anticipate that there are voids anywhere and everywhere. And so you use a product called a screen tube. And so you drill a hole and you have to insert this screen tube thing, which is basically a tube made out of screen, and that will keep the epoxy from just pouring out in mass quantities into the voids. And so that was great, you know, we specified that, and well, finding screen tubes that are 20 some inches deep is very difficult. However, the contractor was able to find some screen tube product that links up and it can make longer sections. There were hundreds of those pins throughout the limestone in the basement. Before they poured that wall, we have a picture of all the pins, and it just looked like a hairbrush sticking out of the wall. There were so many of them. So this picture really doesn't do it justice, because there was a great many more than this. So now we have our seismic loads being transferred down into the concrete sister walls, and we have to put something underneath that. So certainly we could have put in a traditional foundation of, you know, like a spread concrete footing. However, that would have been adjacent to the existing foundation, and the original design drawings said that that original foundation was a cast in place footing, and it was wider than the wall, or shown to, you know, intended to be wider than the wall. So we would have had a hard time getting around that and to transfer the loads to a spread footing under the concrete walls. So we went with a mat slab, and I am very, very glad we did, because as it turned out, they discovered that there was no spread footing under the original walls. It was a rubble infill, a rubble fill, if you will. It's not, I don't know if you can even call that a foundation. However, that's what was there. And considering that the building did not show signs of settlement or other cracking, I guess that rubble foundation fill worked okay. However, if it had been hit by a major earthquake, it certainly would have slipped and moved a lot. And so we had to do something. And the mat foundation was the right choice for that. So here's a plan view of the basement. The brown lines are showing all of the sister walls throughout the basement. So there's quite a few of those. And then the blue is the mat slab. And we used the mat slab throughout the entire basement. And that really had a couple major advantages. First, when you use a mat slab over the entire area like this, you spread out the forces onto a very large amount of soil, which then makes for a very small soil pressure. And with a small soil pressure, it would be a very small settlement. And so by doing this, we could say that our foundation would be very stable underneath of this massive building, even in a significant earthquake. So now moving up into the upper walls of the building with the brick, we did the same pinning type of procedure with threaded rods and very deep holes with screen tubes and epoxy. And there was literally thousands of these. Now looking at a section through the length of the building, I present this overly complicated slide just to draw your attention to this one particular beam in the basement. Here again, the steel frames came down close to the brick upstairs, and downstairs that did not align with where the concrete wall could be placed. And so we had to transfer those column reactions back over to the top of the concrete walls. So we developed this detail that we called our lever beams. So this is a cantilevered transfer beam. Here again, that force would have been too concentrated for the concrete, and so we had to incorporate a second beam in this detail to spread that load out from the lever beam onto a spreader beam onto the concrete wall. So here is a picture on the inside of the building. On the right side, you see that hot rolled steel, or that steel tube, which braces the right side of the window. And on the left, though, you see a doubled stud. And that was actually adequate strong back reinforcing behind the window to brace the window against blast loading. So normally you think of a backup frame behind windows as something as all structural steel. But in this case, with the mass of brick, it only required a small amount of steel to meet the blast loading. And then here is how we attach the windows to that frame. There, you see there that there's a plate between that the window attaches to the plate, and then the plate transfers the blast loading back to the backup frame. And that was what we did at the arches also. We had the arched windows attached to a curved plate, and then the curved plate was attached to multiple straight beams that were set in at the quarter points over the arched windows. So here is a early period wall tie. And the function of this is to keep the walls attached to the floors and keep, everything intact during an earthquake. And it's interesting that they actually knew that they needed this when at the time that this was put in. Our best guess is that this was installed in the teens, so maybe 1915. And it's interesting that even then they knew that they needed to do this. I don't know, it's interesting that they didn't know that they needed to do it in 1898, but that they realized it at some point, and they did this historic retrofit. Now, of course, you know, those holes in that bar are loose, and they would put a nail in that, and it would be loose. And so what they do, they just, you know, put in a few more nails and called it good. Well, not quite good enough. And for sure, those nails were just going into the flooring. They didn't coincide with the floor joist at all. So it was interesting that they knew that they needed it, but maybe at the time they didn't know how badly they needed it. So here is our wall tie that was used on the design. On the left, you see the detail that's actually suggested by FEMA, and yes, they do suggest putting that threaded rod in on an angle like that, which, as you can imagine, would be highly problematic. Your drill bit would not want to start on an angle. You'd have to, you know, get it started and then tip your hammer drill up, and if you hit a void, it would be problems. And if there's any kind of debris in the void, it could grab the bit and really throw the operator's arm. So we chose to put those in straight, and it worked out pretty good. And then the tie was then connected to a clip, which was connected to the endoskeleton. So one other major seismic deficiency was the roof trusses over the core of the building. And there's actually three components to this deficiency. The first being that rod in the middle of the truss. These are tension rods, just stay in tension during static gravity. However, during an earthquake, things don't stay put and don't stay in tension or stay in compression. Things change around and bounce around, so that could have easily come into compression. And that isn't so much of a problem as it is that when it goes back into tension, it would have come from its buckled state back straight, and that would have happened probably rapidly. And when you put tension rapidly onto a tension rod of this vintage, it could very easily break. The other feature that is a weakness of this original truss is the truss connections. Those were simply at rest. And in an earthquake with dynamic forces, things are definitely not at rest. There was no sign of any mortise and tenon. And in fact, there was really nothing holding that together other than its own weight. So that was a major problem. And the final weakness with this is that top cord on the truss that is entirely too long for the size of that timber. And without any bracing on it, it would have buckled, with dynamic loading. So the retrofit for this was fairly straightforward. In that it was in the attic, we were able to do something that was did not have aesthetic requirement. And so the first thing is we put a boxed beam over the top of the trusses to brace the top cord. And you see that's a built-up boxed brace. And that made it easy to take up smaller pieces of dimensional lumber and nail them together and brace that. Rather than carrying a heavy timber up there, it made that straightforward. Then, of course, we put in posts next to the tension rod to make sure that that stayed in its configuration. And then lastly, we put all kinds of straps over the connections and put in a large number of screws to hold them in place. So that was our design, and we certainly had construction challenges. The first was when they removed all the sheathing and the plaster from the walls and the core of the building. These are 3-story bearing walls, and so when they sent this picture to me and asked me, well, what do we do with this? I was a little bit surprised to see that there was no header in there as we would normally expect. And I was told that this is a fairly common header of the period and that they work fine and that I should try the calculations. And in fact, the calculations work out. However, would only pass for static loading. And in an earthquake with all kinds of things bouncing around, this would not have been adequate. So the solution here was to plate both sides of this wall and nail it to death. So there's just a great number of nails holding that sheathing on, and that is the solution here. And part of the historic preservation is to reuse the exact materials in place. So structurally, all of our stuff is usually hidden, and this is certainly hidden. No one might ever see that again. But it just gives me a sense of peace to think that, hey, I reused that header, and I didn't replace it. So on the outside of the building, one thing that was really cool was that we were actually able to use the original attic ventilators. Here on the ridge, that is the original attic ventilator, I was told, from 1898, that they cleaned up and polished and put back on the roof. So also we see the chimneys here, and our original design called for steel tubes to be put inside of the flues, and for the annular space between the steel and the chimney to be filled with spray foam insulation to brace, and that would brace the chimney. However, what we didn't take into account was that these chimneys have very large flue liners in them. And so instead of having, say, a 10-inch by 10-inch squares or flue, we had much larger, like 2-foot by 2-foot squares, and that would have been way too much spray foam, and it just would not have worked. It would have squished around the steel, and it wouldn't have braced it well. Furthermore, the contractor elected to go ahead and demolish the chimneys on the inside of the building, and so there was extremely little holding that up there when I was called to site to look at this. And they literally had like 3 2x4s supporting that entire thing. And so we had to do something different. And, you know, the one potential solution could have been to use concrete instead of spray foam, and maybe larger structural tubes. However, that would have added more mass. And considering that they had basically nothing supporting it to begin with, I didn't want to add any more mass. And especially up high, mass at height and seismic is bad. So the other option that we kind of joked about to start with was, well, we could tear them down and build this all with conventional brick ties and be no problem at all. And then as we got to talking more about other options, it's like, well, that's really the only option that's we could actually, you know, show passes the building code for, you know, design checks. And so we had to call the State Historic Preservation Office and ask, you know, what do you think about reconstructing these chimneys in order to retrofit them? And that's kind of not the goal of historic preservation, but the SHPO said yes, because they are at a high enough distance from the ground that no one would really be able to know the difference. And so we constructed them in the same configuration, and the mason was able to use almost all of the original brick. And certainly it's new mortar, but using the original brick met the goal of the historic preservation of reusing the original materials. So that brings us to our last construction challenge and nearing the end of the presentation. However, this was a real challenge. So on the left, you see the original construction there, and those are heavy timber girders coming in to the column, and they're supported by that cast iron plate, which is supported by the column below. The problem with this is that that plate is simply at rest on the column below. So the figure on the left is showing you the original configuration, and certainly in an earthquake that would have fallen apart. Also, that cast iron column cap was in bending in that configuration, and so bending creates tension stress, and tension, as we know, in cast iron is not good. So that had to be replaced. So our solution is on the right, and pretty simple. We just put a steel tube inside of the column above and a steel tube in the column below and lock that all together so that it's all has to move together in an earthquake. The real question was, okay, well, this is great, but I don't have any idea how they're going to get that in there. I mean, there isn't a hole in the side of the top of the column capital to just like magically insert that, right? So we thought, well, maybe they'll shift one column up and shift the other one down. And what they ended up doing was they actually shored the entire building, the entire 3-story building, took out all of the columns and put them back in one piece at a time, stacking them up with this. Pretty major shoring project, but they accomplished it. So that brings us to the end of the presentation. However, I have a challenge for you. You know, like as I explained, I grew up on a farm and had extremely little value for historic structures. Through this project, I learned a great amount of appreciation for historic things. And when I first came to this building, we were stuck outside. The building was locked and we couldn't get in. And so we were all gathered on the front step. And I remember looking down and I saw a cast iron thing that was bolted to the step. And I didn't know what it was. And I just thought it was kind of neat. You know, I saw the manufacturer's name and the date was cast in there. I didn't really think a whole lot about it until later on in the project. And thinking about all the other historic things in this, I really got to wondering what that cast iron thing was. And so I did a little bit of research on my own, and I found out that it was a boot scraper. Now this is a cavalry barracks, so that is just so historic that you know, they needed a boot scraper because you best not come back to the barracks with a horse manure on your boots. So, and that for me is an example of the appreciation of the history that I experienced in working on this building. And so as we close, my challenge to you is this, is that we consider the historic value of things. And I am not advocating for preserving everything on the historic registry. However, I challenge you to think about the historic value of things and make the best decisions we can. Thank you.
That's great. Dave, I really want to thank you for the presentation today. I enjoyed it a great deal. And I'm going to open it up here for any questions anybody has for Dave.
Hey, this is Daphne. Dave, I have a question. Can you elaborate a little bit, David, on what the initial budget was from your client, the government, and what it ended up being? Can you talk a little bit about that?
The actual construction budget was $7.2 million, and it did not change throughout the life of the project. The design fee did a little, but not much.
So the project was, you dealt with issues on the budget. You must have encountered quite a lot of unforeseen conditions and things.
Absolutely. The major one was Seismic. The programming did not call for the Seismic retrofit at all. It identified the anti-terrorism force protection measures, but it did not identify the Seismic retrofit. So starting in on this project early in Type A, we identified that and we made that known. However, we were forced to continue, and it wasn't until Type B when we got the programming changed to incorporate the Seismic. And so when you're in Type B with everything else, to add in all this steel, it was a monumental feat in and of its own.
So where did the budget was still the same if it was fixed? Where were the cuts made on the interior? Where were the cuts made to be able to make it work?
Well, I don't honestly know. The interior finishes were not high architecture. They were basic office finishes. And so that might have been some source of that. I can't tell you. Otherwise, I don't really know. $7.2 million is a lot. So maybe it was over budgeted. I'm not sure.
Okay. And on the interior, can you also elaborate why were the finishes taken off of both sides of the interior walls? Usually in historic preservation projects, especially if you have a mural on one side or you're trying to preserve a tile work or something, we'll keep one side and then we'll do all the work on the other side. Why was it taken off on both sides?
Well, that may have simply been that there wasn't any historic value to either side, and it was plaster, and it was most probably cracked on both sides. And so I'm sure there's preservation measures to be applied to plaster. However, the emphasis here was really on the exterior and really on maintaining the historic district. There is like a 40-acre parade grounds in front of this, which they have different events and things, and they're so really the emphasis was, okay, we know that we don't have the money to do historic preservation for everything in this building, so let's do everything we can to preserve the exterior appearance from the parade grounds.
Thank you.
Anybody else have any questions?
Yeah, can you hear me? All right.
Yep.
Yep. Hi, David. My name is Bernie. I'm actually from Parsons. I have a question about the blast loading. I saw that the one of the slides shows the HSS on one side of the window and some metal studs on the other.
Yes.
The question: what was the actual pressure on those blast load, and what was the governing design? Would it be the rebound or inbound type pressure loads?
Well, with the mass, you really have extremely little outbound, so it would have been inbound. And as you know, with blast loading, you don't have any pressure, unless you use the F2248 approach, and we didn't. We used the blast analysis with S-beds. And so I don't know what the pressure would have been in an equivalent type of analysis. Trying to find that slide.
So what was the pressure that was put in on S-beds?
Well, you put in a 55-pound bomb at your standoff distance, and the standoff distance for this building was 26 feet.
Okay.
Or 33 feet, I'm sorry.
Thank you.
Dave, Hugo Gardea asked the question about the fact that many of this type of barracks are found throughout the country. Has anybody else has the solution that you've prepared, has that been applied to any other structures?
I don't know. This is the only one I've been involved in.
Okay, and I guess that's I mean, in fact, it's interesting to me that when Daphne asked about the budget, I mean, obviously somebody must have known what they were doing when they developed the budget for this project, and obviously you got a good contractor. I mean, that's just amazing that it was able to be completed within the budget. So. I know we're at the end. We're just 1 minute over our normal time. Unless there are additional questions. In fact, I would encourage anybody to send their questions on to Dave. I want to thank Dave for a great presentation. I think one of the things that I took away from this is that it's an interesting. It's interesting to me that this historic structure has provided you with some amazing opportunities for innovation. You know, in all of those structural solutions that you applied. You know, the lever beams, the wall ties, the roof trusses, and you know the sister walls and the mat. I mean, I just think these are just great innovations that would not normally be applied to a building. So I think it's very impressive stuff. So with that, I think we'll close things up. Again, I would encourage you to pass on your questions. If you have any additional questions, back through the APC, and we will certainly get those answers for you. I want to, again, express my appreciation for all those who participated and for David Cockram's wonderful presentation today.
Dave, JJ here. Just one reminder to everybody on the line. If you need the AIA HSW unit, if you don't have your AIA number before, who do we need to send the information to, Dave?
We would send that to Jose and or to me, either one, and we'll make sure that you get the AIA credits for this.
I mean,
that's good. Good reminder.
I guess the majority of the folks on the line, like myself, you already have the AIA number, so you don't really need us to send it to you anymore. But for the guys,
for those who have not been on in the past, that's correct.
Okay.
Yes.
All right. Thank you.
All righty. And I saw Bernie indicated a request for a copy of the slides. Dave, if you could send me a copy of your slides so that we can post them on the website, I'd hugely appreciate that.
Sure, no problem. Also, specifically with the change in the UFC on anti-terrorism force protection, if anyone is studying the new version and has edits to those slides, I would greatly appreciate that. I haven't been involved in a project yet where I have done another ATFP application, and so these are going to be dated soon. And if anyone wants to help modify those, I'd appreciate it.
Excellent. All righty, very good. Again, this program, this webinar has been recorded, will be available. I'll send you a copy of it, David, and it will also be available on our web page. So again, I want to thank everybody, again, especially David, and I wish everybody a great week, and we will see you again in 3 months.
Thank you.
Thank you.
Bye.
Thanks so much.
Thank you.
Thanks.
Thank you.
Bye.
Bye.